Hey everyone, and welcome back for another deep dive. You guys sent in some pretty intense stuff this time around.
Yeah, this one is a bit of a brain buster.
Yeah, lots about energy reactions, entropy.
Hmm.
But that's right. That's what we're here for, to make sense of it all.
That's right. We're going to unpack these core ideas of thermodynamics.
Exactly. So whether you're cramming for a chemistry exam or just like love geeking out about science, you've come to the right place.
And by the end of this, you'll look at your morning coffee or even a messy room in a whole new light.
Ooh, I don't like it, foreshadowing. Okay, so to really dive into thermodynamics, we need to start with the basics.
Yeah, you got to crawl before you can, run a marathon.
Exactly. So first up, the idea of a system.
A system is simply the part of the universe we're focusing on. It could be anything, like a beaker full of chemicals
Yeah.
or a whole ecosystem.
Okay, so like if we're thinking about a fish tank,
Right.
the
right.
fish, the water, the plants,
Huh.
that's our system.
Exactly. And
Yeah.
everything else.
Yeah.
The room, the air outside, that's the surroundings.
Got it. So we're drawing a boundary to define what we're studying.
Precisely. And once we've got our system defined, we need to talk about its state.
State? Like, is it solid, liquid, gas?
Well, kind of. It's more about describing the conditions within the system at a specific moment in time.
Okay, so like with our fish tank, we'd look at the water temperature, the pressure, the amount it
Yeah.
dissolves oxygen, stuff like that.
Exactly. Those properties define the state of the system right then and there.
It's like a snapshot of what's going on inside.
Perfect analogy. Now, here's the thing. Systems don't just stay static. They change, right?
Yeah, like what if we crank up the heater in the room? The fish tank's going to warm up.
Exactly. And that brings us to a fundamental question in thermodynamics. What happens when a system gains or loses energy?
Ooh, yeah. Where does that energy go?
That's where internal energy comes in. It's the total energy stored within a system.
Okay, so kind of like a system's hidden energy reserve.
Precisely. It's all the energy locked up in the molecules, their motion, their bonds, their everything.
So internal energy is like the sum total of all the energy tucked away inside.
Exactly. And this energy can change
How so?
through heat work or transfer of matter. Let's start with heat. It's the transfer of thermal energy between objects at different temperatures.
Okay. So like when I heat up a pot of water on the stove, the heat from the burner flows into the water, increasing its internal energy.
You got it. Heat flow always goes from hotter to colder, trying to even things out.
It's like nature's way of sharing the warmth.
Exactly. Now let's talk about work. It's the energy transfer that happens when a force causes a displacement.
So like pushing a heavy box across the room, I'm doing work, and that energy is transferred to the box.
Precisely. Work is energy in motion.
And this is where Joule's experiment comes in, right?
Exactly. Joule showed that you could raise the temperature of water not just by heating it directly, but also by doing work on it.
Like churning it with paddles.
Right. That mechanical work gets converted into heat, increasing the water's internal energy.
So work and heat are like two sides of the same coin.
I like that analogy. They both change internal energy. And this brings us to the first law of thermodynamics.
Which is, drumroll please,
Energy cannot be created or destroyed, only transformed from one form to another.
so it's like a cosmic accounting system. The total amount of energy stays the same. It just shifts around.
Precisely. The first law is the bedrock of thermodynamics.
Okay, first law locked in. Now let's dig a little deeper into those energy transfers. Heat and work. They seem pretty different, like fire versus weightlifting.
Well, on a fundamental level, they're both forms of energy transfer. But there are some important distinctions. In thermodynamics, we often focus on pressure volume work.
Pressure volume work.
Yeah.
Okay, break that down for me.
Imagine a bicycle pump. When you push down on the handle, you decrease the volume of the air inside, and the pressure increases. You're doing work on the system.
So compressing that air takes work. Makes sense. And what about the opposite? Like when air expands to inflate a balloon?
Exactly. The expanding gas does work on the balloon pushing against its walls.
Okay, I'm starting to see how pressure and volume are linked to work.
Now here's where things get interesting. The concept of reversible processes.
Reversible processes, like rewinding a movie.
Not quite. Imagine inflating that balloon very slowly, adding tiny puffs of air at a time. Each tiny puff is essentially at equilibrium. That's a reversible process.
So slow and steady wins the reversibility race.
Exactly. Versus just blowing it up all at once, which is irreversible.
Got it. So reversible processes are all about those tiny equilibrium steps.
Now let's switch gears to heat transfer. Remember, heat always flows from hotter objects to colder ones.
Like my coffee getting cold way too fast, why can't it just stay hot forever?
That's the second law of thermodynamics in action. but we'll save that for later.
Okay, cliffhanger. But before we move on, I have a question. A lot of the reactions we see in a chemistry lab happen in open containers, not sealed systems. How does that affect things?
That's an excellent point. And it brings us to another important concept, enthalpy.
Enthalpy.
Okay, I'm ready.
Enthalpy, represented by the letter H, is a thermodynamic property that takes into account the internal energy of a system plus the energy associated with the pressure and volume of the system.
So it's not just the energy inside, it's also the energy needed to push against the atmosphere. Precisely. And enthalpy is super useful when we're talking about reactions happening under constant pressure, like in an open beaker.
So for most lab experiments, enthalpy is our go-to energy measure.
Exactly. And it's particularly helpful when we talk about phase changes, like melting, freezing, boiling.
Oh yeah. Those transformations involve energy changes even though the temperature stays constant.
Right. The energy involved in those phase changes is directly related to enthalpy. We have specific terms like enthalpy of fusion for melting, enthalpy of vaporization for boiling, and enthalpy of sublimation for going straight from solid to gas, like dry ice.
Okay, so enthalpy is the key to understanding those phase change energy mysteries.
You got it. It's amazing, isn't it, how much energy goes into those everyday transformations?
It really is. And we've been talking about enthalpy a lot, which is super useful for reactions at constant pressure.
Right, but sometimes we need to think about energy changes under constant volume, like in a sealed container.
Okay, so different conditions, different energy considerations.
Exactly. And that brings us to another important concept, internal energy.
Internal energy. I thought we already covered that.
Well, we touched on it briefly, but it's worth diving a bit deeper. Internal energy, represented by the letter U, is the total energy contained within a system.
So it's like all the energy locked up inside, those molecules bouncing around, vibrating,
Great.
rotating, doing their thing.
Exactly. It includes all forms of energy within the system, kinetic energy, potential energy, chemical energy, the whole shebang.
So internal energy is like the system's total energy bank account.
I like that analogy. And as we discussed earlier, internal energy can change through heat work or transfer of matter.
Right. Heat flow work, done matter, moving in or out, all affect the internal energy balance.
Precisely. Now let's revisit those adiabatic processes we mentioned, where no heat is exchanged.
Yes. Those thermodynamic fortresses, where heat can't sneak in or out.
Exactly. In an adiabatic process, the only way to change the internal energy is by doing work on the system, or letting the system do work.
Okay, so back to our trusty bicycle pump. If I compress the air, I'm doing work on the system, increasing its internal energy.
You got it. And if the system expands like inflating a balloon, it's doing work on the surroundings, decreasing its internal energy.
Makes sense. So work done on the system, energy up. Work done by the system, energy down.
Now remember that equation for calculating work during expansion or compression at constant pressure?
I think it was something like work equals pressure times change in volume.
Close. It's actually W weighs PEX-EV work, W equals negative external pressure, PEX, times the change in volume.
Right, the negative sign. Because work done by the system is negative.
Exactly. It's a bit of a convention, but it helps keep track of energy flow.
Okay, convention noted. But all this thermodynamic stuff, it's got to have some real-world applications,
right?
Not just equations and abstract concepts.
Absolutely. Thermodynamics is all around us, from the engines that power our cars, to the refrigerators that keep our food cold, to the batteries that run our devices.
Whoa. So thermodynamics is like the science behind modern life.
In a way, yes. It helps us understand and optimize energy transformations.
So like designing more fuel-efficient engines or more powerful batteries.
Exactly. And let's not forget about those amazing refrigerators.
Yeah. They seem to defy the laws of physics, keeping things cold when everything wants to warm up.
Well, not quite defying the laws, but cleverly using them. Refrigerators use work to transfer heat from the cold interior to the warmer surroundings.
It's like a thermodynamic uphill battle.
Precisely. The compressor in a refrigerator does work to move heat against its natural flow.
It's like we're tricking nature with thermodynamics.
And enthalpy, remember, our trusty state function plays a crucial role in many practical applications.
Right. Enthalpy is all about that total energy package.
Yeah.
Especially at constant pressure.
Exactly. And it's particularly useful in chemistry when we're studying reactions, like dissolving a salt in water.
Oh yeah. Sometimes those solutions get hot or cold depending on what's dissolving.
The enthalpy change tells us whether the dissolving process absorbs heat endothermic or releases heat exothermic.
So it's like a clue to the energy drama happening at the molecular level.
Exactly. And let's not forget about phase changes. Enthalpy is our guide there too. Remember enthalpy of fusion, enthalpy of vaporization? Enthalpy of sublimation?
Yeah. They're all about the energy needed for those amazing transformations.
Right. And remember how we talked about standard states? It's all about having a common reference point for comparing energy changes.
Makes sense. It's like setting the ground rules for the energy game.
Precisely. And when we talk about standard enthalpy of formation, it's the enthalpy change when 1 mole of a compound is formed from its elements in their most stable states at those standard conditions.
Okay, so it's like the energy blueprint for building a molecule from the ground up.
Exactly. And knowing those standard enthalpies of formation, we can calculate the enthalpy change for any reaction.
It's like having a thermodynamic recipe book.
Right. And Hess's law, our secret weapon for multi-step reactions.
Ah, yes. Hess's law. It's like our energy accounting trick for figuring out the total enthalpy change, no matter how many steps it takes.
Yeah, but there's another piece of the puzzle we need to talk about.
Okay, I'm intrigued. What's next?
Enthalpy is great for telling us about the energy of a reaction, but it doesn't tell us the whole story. Sometimes reactions that release energy don't happen spontaneously. And sometimes reactions that require energy do happen on their own.
So there's more to spontaneity than just energy.
Absolutely, and that's where entropy comes in. It's all about disorder or randomness.
Disorder, so like, my messy room has high entropy.
You got it. A messy room has more possible arrangements of things than a tidy one, so its entropy is higher.
Okay, so entropy is like a measure of how many ways you can arrange a system.
Precisely. And the second law of thermodynamics tells us that for any spontaneous process, the total entropy of the universe must increase.
So the universe is constantly getting messier.
Well, it's not necessarily about mess in the everyday sense. It's more about the spreading out of energy and the increase in possible arrangements of particles.
Okay, so more options, more entropy.
Exactly. Think about a deck of cards. A shuffled deck has higher entropy than a perfectly ordered deck because there are so many more possible arrangements.
Right, so shuffling a deck of cards is a spontaneous process because it increases entropy.
And the same principle applies to chemical reactions. If a reaction produces more gas molecules than it consumes, entropy increases because gas molecules have more freedom of movement than molecules in a liquid or solid.
So reactions that create more chaos tend to be favored.
That's a good way to think about it. But remember, entropy changes can also arise from changes in temperature, the number of particles, or the structure of molecules.
Okay, so entropy is a multifaceted concept.
It is. And as we said, the second law tells us that for any spontaneous process, the total entropy of the universe must increase.
But how do we actually calculate this entropy change?
Well, for a reversible process, the entropy change of the system is simply the heat absorbed divided by the temperature.
So if a system absorbs heat at a constant temperature, its entropy increases.
Precisely. And the entropy change of the surroundings is related to the heat released by the system. Remember, heat flows from hot to cold.
Right, so whatever heat the system loses, the surroundings gain.
Exactly. To get the total entropy change, we add up the entropy change of the system and the entropy change of the surroundings.
Okay, that makes sense. But what about reactions or processes that aren't reversible? How do we figure out if they're spontaneous?
That's where our friend Gibbs free energy comes in. It takes both enthalpy and entropy into account.
Ah, yes, our thermodynamic crystal ball.
Exactly. The equation is Hg equals Ht.
So we're weighing the energy change against the entropy change with temperature as the deciding factor.
Precisely. And the sign of Ag tells us everything. If it's negative, the process is spontaneous. If it's positive, it's non-spontaneous. And if it's zero,
Equilibrium.
you got it.
Wow, this whole deep dive has been a wild ride. I feel like I have a much better grasp on thermodynamics now.
It's been a pleasure exploring these concepts with you.
Likewise. And to all our listeners out there, thanks for joining us on this thermodynamic adventure. Keep those brains buzzing, and we'll catch you on the next deep dive.